This is problem 1148. It's on page 635. It says repeat problem 1133 if the column has an initial crookedness of 1.25 inches. So the only thing we're given so far is the 1.25 inches of crookedness. Page 634 contains problem 1133 that was referenced. A hollow rectangular steel tube, HSS 3 by 2 by quarter, is used to support an axial compressive load. The tube is 13.6 feet long and rigidly fixed at each end. It is made from ASTM A501 hot-formed structural steel. Bless you. Compute the allowable load on the column for a design factor of 3. So the design factor is 3. The length is 13.6 feet. It's a rectangular tube, 3 inches by 2 by quarter wall. And the material is ASTM A501, which is a structural steel. Okay, now it's fixed at each end. So let's just go ahead and calculate the effective length. Because we know we'll need it, right? The effective length, well, if it's fixed on each end, what factor do we use? We haven't seen this one yet, so we'll have to go look it up. Page 607. Fixed in columns, how much of the length is the effective length? 65%. So we want 65%. Now my guess is we'll have to work in inches. So go ahead and multiply 12 inches by 1 foot by the 13.6 feet that we're given. And let's see the length of this column in inches. I'll just erase it once you tell me the number.
163.2.
Sounds reasonable. Okay, so assuming that's right, 163.2 inches, if we multiply that by the 65%, what's the effective length of this column?
$106.08 inches.
Okay. All right. Now let's go back to the HSS, the steel structural tubing, page 704, since we're in English units, and look up the cross-sectional properties. We'll be referencing row N. And in all of these methods, we've had to calculate the slenderness ratio. We should have to again. Let's see. Yeah, just for your reference, turn quickly to page 625 if you would. Notice in equation 1119 we have to calculate the critical load, which is found from the Euler formula. So basically we have to solve problem 1133 first, then we'll be able to solve problem 1148. Okay? So to do that, we'll have to calculate the slenderness ratio. The slenderness ratio is the effective length divided by the radius of gyration. And they do give us the radius of gyration. So on row, what did I say, N, looks like the minimum radius of gyration is 0.751 inches. Everybody see that on page 704? Okay, so 0.751. So please plug that into your calculator and tell me the slenderness ratio.
131.25.
Trying to write inches, this is non-dimensional. 141.25 seems reasonable, okay. Now let's calculate the critical load, and let's see, looks like we will need the yield strength as well. We'll get all that in a minute. Well, let's calculate the critical load from the Euler equation. I want to point out one more thing. Go to page 614 and 15. You'll notice that a summary, a nice summary is listed here. It's a step-by-step procedure, which is always handy. We're going to use equation 11.4, that's page 615. The critical load is equal to pi squared EA divided by the slenderness ratio squared. Doesn't look right. Let me go back and reference the equation. That is correct. Okay. And it looks like I should have written down some more properties while I was back there looking at that beam. We've got R so far. R is 0.751 inches, but how much cross-sectional area was there? Please go back and look it up if you would. While you're doing that, I'll go to the material properties. Anyone look up the cross-sectional area?
1.97 inches squared.
So 1.79 square inches. Thank you. All right?
97. 97.
97, thank you. Okay, let's see. So we have pi squared. E again is going to be 29E6 psi. 1.97 square inches divided by the slenderness ratio, 141.25 squared. Okay, so the critical load will be in pounds, if someone will put that in their calculator.
At 28,260.3.
28,000, how much?
260.3.
60.3, and that would be pounds force, right? Because the square inches went away. Okay, so there's the critical load. Now if we go to page 625, we should have everything we need, I think, in order to calculate this. Now, your author notes that what I'm going to do is just write down the constants C1 and C2. It looks like C1 is negative 1 over N times the yield strength times A plus quantity 1 plus AC. And I don't know what AC is yet. We'll find out in a minute. Divided by the radius of gyration squared times the critical load. So that should be C1. C2 should be the yield strength times the cross-sectional area divided by the safety factor squared. No. Times the critical load. Okay, so there are the constants C1 and C2 so that we can plug in and solve for PA. PA will end up being 1/2 of negative C1 minus root C1 squared minus 4C2. This is just a quadratic equation, so it shouldn't be too bad. Now, what is AC? C is the distance. Okay, the crooked column formula allows an initial crookedness A to be considered. So this must be what was given back here. That was the initial crookedness. And then C is the distance from the neutral axis of the cross-section about which bending occurs to its outer edge. So what would that be? Let me sketch it over here. So essentially, there's what we're dealing with. We've got dimension on this side of, what is this, 3 by 2, so 3, 2, these are all inches, and then nominally a quarter wall. These are all nominal dimensions. But then C is the distance from the neutral axis to the cross. Now, of course, the neutral axis passes through the centroid. Okay. From the neutral axis of the cross section about which bending occurs. Which axis is the one where bending occurs? It's this one, right? The beam's going to bend this way. Okay, so we want the distance from that neutral axis to the outermost, that's this. So that distance would simply be 1 inch. Does everybody see that? Okay. So now we should be able to calculate all this stuff. So basically what we got from this is that this is 1 inch. Now the radius of gyration, did we ever calculate that? We wrote it down. So there it is. So I think we've got everything we need. Let's plug it in and find out. Okay, -1 over n. N is 3. The yield strength is 36 KSI. I went and looked it up while you guys were looking for cross-sectional area properties. So the 36,000 PSI for SY. A, the cross-sectional area was 1.97. You know, we're going to run out of room if I don't eliminate the units. And so this is somewhat dangerous, but I know this is PSI, this is square inches, so we should have pounds for the first term. So that's pounds force. As long as this is pounds force, which it looks like it will be, because that's the critical load there. And notice how we have inches times inches over inches squared, so this will be dimensionless. So it looks like we'll be okay. So +1 plus A times C. If C is just 1 inch, then we'll just end up with A, which is 1.25, at least numerically, divided by R squared, so 0.751 squared. And if I'm off the video, I apologize. The critical load, 28,260.3, should end it off, and now we should have everything we need to calculate C1. So please plug that into your calculator. If you can't read my writing up here, just let me know. I'll tell you what the numbers are. While you're calculating that number, I'll go ahead and write these a little clearer, hopefully. Anyone have a number for C1? Or for C2?
-53,937.9. So 938.
Whichever. What would the units be for C1? Pounds. That number looks reasonable because we have about 2 times 36,000, so that's about 70,000. This number is going to be roughly 2 times 28,000. So let's see, where were we? 70, say 50, 120 divided by 3, 60. That makes sense. Well, no, 120 divided by 3, that'd be more like 40. Still, I rounded my numbers quite a bit, so that'll be all right. How about C2? And these aren't the answers, but I'm putting a box around them because we're going to use them down here. So we'll lose track of them.
This one's supposed to be a really big number.
It's going to be big, yeah, because we've got 36,000 times 28,000 or so. So put it in scientific notation, it's fine. So I'm going to have units of pounds force squared.
.2 times 10 to the 8th.
Can you give me a few more decimal places?
2.2269.
times 10 to the 8th, and that would be pounds 4 squared. Anyone second that? All right, so now we should be able to calculate the allowable load. It's 1/2 of negative C1, so negative of a negative is positive, 53,937.9, minus, now you have to be careful, when you take the square root of something, there's a positive and a negative square root. So why they've got a negative here, I don't really know. I would say you'd end up with plus or minus, right? Because if you take the negative square root, negative of negative is effectively a positive. So anyway, so C1 squared, 53,937.9 quantity squared, minus 4 times 2.2269 times 10 to the 8th. There we go. So what I would do is, first of all, figure out this number, right? 53,937.9 squared minus 4 times 2.2, etc. times 10 to the 8th. Take the square root of it, and we'll write down that result here. So just give me this bit to start. Yeah, we could have just made a spreadsheet. Probably would have been better. You guys probably hated spreadsheets when you first started here. Now hopefully you love them because you realize how useful they are and how much work they save you.
44,928.1.
24,928.1.
44.
44, thanks. Okay, now that, if we take negative, we'll get the smaller load. That's what we want, right? So we have to choose the negative sign. Does everybody see why? We want to get the smallest allowable load. So now take 53,937.9 minus 44,000. You could just do 54,000 minus 45,000 if you wanted to save yourself some time. And it's not too bad. And then cut it in half.
4,500.
4,500 pounds. Anyone second that?
Yes.
At this point, who cares, right? 4,500 pounds. That's the highest load that this column that's loaded off to the side could take. One more thing before you go, before you get too anxious here. What was the critical load? 20,000. Look what a difference it makes when you have a crooked column to start. It makes a big difference. Any questions, comments? All right.